Okay, so good afternoon, everyone, and welcome to the seventh day of this faculty development program on quantum sensing. And today lecture is scheduled on this quantum measurements in continuation of these previous lectures. And the speaker for today's session is Dr. Ashok Babu from Department of Physics, uh, IIT Dharwad. I hope all the participants they are now familiar with Dr. Asok Babu. And yesterday session goes very well, and there were so many queries. And I'm thankful to the speaker for me responding the query during the lecture also. So I hope this will be like in better understanding related to this quantum measurements. So now I request Sir uh, for the lecture.
Hello, Abasti sir, can you hear me?
Yes, yes, perfect, sir.
Okay, sir. Thank you. Thank you very much for the opportunity and the introduction. So the participants are 150. I'll just set up things. By
Sure,
that
sir.
time, people will come.
Sure, sir. Sure.
Yeah, hello everyone. I think right. We can start, I guess. So let's see how many are there.
190.
Yes, yes, sir. Yes, sir. Yeah, we are right. So very good morning, very good afternoon to all the participants. Uh, Once again, thanks, a big thank you for tuning up for this session for today. Right. So yeah, I'll use the PPT wherever it is possible, and also I'll use my Blackboard hand notes. Okay, it is better in that way, like every time. Okay, so today's topic is quantum measurements and standard quantum limits. Okay, how far we can do the measurement, that is what we will do. And yesterday there were some questions were asked. Why do we see the disturbance when I make a measurement on the quantum system? Okay, that is a question being asked several times, right? It is actually agreed. Okay, it's a fair question to be asked, right? So we will try to answer that particular question in today's class. Okay, right? By answering that question, most of the doubts would be clarified, right? Okay, right. And yeah, 1 minute. Yes, why? Now let me go to the next slide, which answers our question. Okay, right? So as you can see here, right? What you can see is foundations of quantum measurement, the nature of measurements in quantum mechanics. Okay, the key principle or a key idea which I would like to emphasize here is in classical mechanics or classical physics, real physics. Okay, right? What you see is measurements can be made arbitrarily accurate without disturbing the system. Okay, what I mean is in a real world, if somebody is standing at some position, I can accurately find its location without disturbing his position. Or somebody is running to measure his speed, I don't need to hold him. Okay, right? I don't need to have a device which go and interact with him and gives me what is his speed. Nothing. I use light as a means. So there is a light going from somewhere source and hits his body and reflects back to my eye or my device. Let's say there is a speedometer. It will find the location from where the light is coming. It will figure out what is this location at a given time. After some time, where it has moved, and it finds out within a time duration how much it is moved, and then it will give me the speed of that particular person or a vehicle. Okay, speedometers, how they work. The police uses, traffic police uses in the highways. Okay, and now that is what in a real scenario. Okay, now if you go to the this classical system, there is some fancy word called perturbations. Perturbations in the sense, while measuring, I will disturb the system by making small changes. Okay. To know about the system, I need to slightly disturb it. Then only I will know the ability. So that is the quantum physics process. So such perturbations are never going to exist in the classical physics. Okay. To know, for example, to know weight of something, I'll pick it up and put it on a weighing balance. Okay. And it will not disturb the weight of that particular object in classical world. If you go to tiny and tiny and tiny things, probably it might disturb that. Okay. But at a classical macroscopic level, it will not disturb. That is what classical physics is saying. In classical physics, there is no perturbations. If there are any perturbations, it is negligible and can be ignored. Okay. Right. So it can be ignored. Okay. Let me see if my voice. Yeah. Right.
Yes, sir.
Yeah. Sorry. And one more thing is, sometimes if I feel like in real world classical physics, if I feel like I have not made the measurement accurately, I need to do the measurement several times to figure out what is the exactly I am measuring. Okay, that is what a sequential measurements yields identical results. Means if somebody is standing somewhere far, okay, in one glance I will not able to figure out who he is. Okay, what I'll do several observations. Okay, so those several observations are not going to sequential observations or measurements not going to affect this system, and moreover all those observations will give me exact result, identical result. Okay, so that is the classical physics for you. Okay, means the real world physics for you, a real world scenario, or you can say uh, world scenario, classical physics, uh, whatever I can have on any other description. Macroscopic world. Macroscopic means large. Okay, but the story is different when it comes to quantum physics, which is microscopic world. Okay, microscopic world or quantum domain or quantum regime, people use different notions. Okay, so here measurement induce non-negligible disturbances, very important. Okay, so measurement is not like not fiddle, is the notion of not fiddling with the equipment. Sorry, actual system is nowhere exist here. So the system is there, quantum system is there. If you try to do something with a quantum system, you know what happens? It is going to disturb the quantum system. Okay, right? So let me just do one thing. Okay, yeah, right. It is definitely going to disturb the quantum system. And one more thing is, the act of observation changes the system state. Okay, not only just minute disturbance, it is completely change the system state. Okay, that we know, we have seen yesterday. Okay, why it is, we will see. There is a description here. And the measurement apparatus and the system, okay, cannot be separate from each other. Okay, right? So the measurement apparatus and the system are actually joined. They are together. They exist together. So what is the measurement apparatus? It is something called operator. It's called quantum operator. Okay, we'll come to that. What is a quantum operator? Okay, a system for be a qubit for me. Okay, right? So these two things are actually, it's like they're connected to each other. We cannot say the measurement operator is a thermometer, I can use it and then put it somewhere else and there is no connection between thermometer and the patient, okay, in real world. But in quantum world, that is not possible because they are together. This they're somehow related to each other. We will see that what is that relation. Okay. Now, example here. Okay, why the quantum systems gets disturbed when I make a measurement? So that is the example given here. Okay, just to consider a simple example of electron in a hydrogen atom. Okay, right? So let me remove this. Okay, let's put that together. Now let's take a situation. What is the situation I'm using? Let's take a hydrogen atom. There is only one electron. Remember, for hydrogen, only one proton, electron. Okay, right? Now, this electron, which is there, rotating about the nucleus. How far it is located? As you can see here, the radius of orbit for hydrogen atom is, okay, 10 to the power of minus 10 meters, 1 angstrom. Okay, so yeah, right. So one angstrom. So this 1 angstrom, you know what happens? Means electron is located 1 angstrom away from the nucleus. Okay. Now the issue is, if I want to find that electron is in that location or not, okay, right? What I should do? I should send a light which goes and interacts with that electron and comes back after reflection and hits my device, which picks it's a device having a detector which picks, okay, right? So let me use, I'm sorry. So electron detection, okay, in a hydrogen atom. That is the target for me right now. Okay. Now you see nucleus is there and electron is around. Okay, it is rotating. Now you see the distance between electron to the nucleus is 10 to the power of minus 10 meters. That is 1 angstrom. Okay. Now I have to send the light. Okay. So the light is in such a way. Okay. It should not go and interact with some other electron. Okay. Right. Should not go and interact with something else. Okay. And not get the, like, carry the information of that part. Okay, right? Okay, so okay, fine. So let's say if I send a light whose wavelength is very small, then it will go and interact with this. If the wavelength is of the size of this nucleus, distance between nucleus to the electron, you know what happens? The lambda is, if the lambda is of the size of 1 angstrom, you know what happens? This lambda electromagnetic wave goes and even interacts with this nucleus. And actually it gives me the information of nucleus in the case of giving electron information. Moreover, that is one problem. One more problem you just see. Okay, let's say wavelength required is anything less than 10 to the power of minus 10 meters. Okay. Uh, right. Uh, yeah. Now what happens? The corresponding energy for this wavelength, if you just see it, corresponding wavelength, which is what? which is lambda is 10 to the power of minus 10 meters, and the corresponding frequency mu c by lambda, which is 10 to the power of 8 by 10 to the power of minus 10, which is about 10 to the power of minus 18 hertz. Okay. Now, if you find the corresponding energy, which is E is equal to H into mu, which is 10 to the power of minus 34, I'll just write into 10 to the power of minus 18 hertz. Okay. Now, if you just see the amount, okay, right? Sorry, this is a Hc by lambda, okay, right? So 10 to the power of minus 34, 10 to the power of, okay, so here it's not c by lambda. Yeah, mu is c by lambda for sure. Okay, so we will be getting something Planck's constant is minus 34 for sure. Okay, 3 point. Okay, so this is, I think there is some mistake somewhere, but anyway, so this comes out to be 10 to the power of 4 electron volt. What is EV? E is 10 to the power of minus 18 coulomb. Na? Electron charge, roughly 1.6 into 10 to the power of 18. So we should be getting of some that number 10 to the power of minus 34 into 3. Okay. This is positive, huh? Yeah. Right, now it makes sense. Okay, so 10 minus 34, 34 minus 18, which is 26. Okay, from 20, okay, that is 16. From 16, if I remove, okay, if I, this is 10 to the power of 6 minus 16. If you add uh, if you add 200, yeah, we ignored the other constants. Okay, so 6.2 or something here, 3 is something here for radius, sorry, velocity of the light. So that comes out to be another 100 extra. So this 10 to the power of 6 electron volt. So energy required roughly 10 to the power of 6 electron volt is required to just measure an electron inside a hydrogen atom. Okay, that's fine, right? Okay, then now you just see the nature of the hydrogen atom. You know, to knock the hydrogen atom out of electron out of the hydrogen atom, the hydrogen atom ionization energy, hydrogen atoms ionization energy, if you just notice, okay, how much it is? It's just a 13.5 electron volt roughly. And what are we talking about? We are talking about 10,000 electron volt required to just measure an electron. But just with 13.5 electron volt, what happens? Electron and hydrogen atom is so small, that is the smallest. Okay, so by the time you send a light to just see the electron, you know what electron is doing. So what the light is doing, it is just knocking the electron out of the hydrogen atom. Okay, so what I mean is the light whatever I am sending onto the hydrogen atom, as if instead of just hitting and coming back to my eye or to my device, light, it is just to just remove the electron out of the atom. Okay, so that is what happens, because you know the energy required for knocking the electron out of the hydrogen atom is barely just 13.5 electron volt. To just distinguish between electron exist in the hydrogen atom away from nucleus about 1 angstrom distance, how much energy required? Only 13.5 electron volt is required. Because of this you can conclude, okay, the very act of measuring of quantum systems may seriously disturb them to a greater extent. Okay, the measurement disturbs the system. Okay, to a greater extent, okay, at quantum mechanical regime. Okay, so we just took for hydrogen atom. You can take any other atom, okay, roughly the size more or less little bit bigger, but what the result what we see is the same. Okay, so that is the most important conclusion. This is why if I make a quantum qubit, the qubit becomes a single bit or a classical bit when I make a measurement. Okay, I hope you understand and appreciate what is the story behind the measurements collapsing the quantum systems when I make a observation. Okay, so let me go to the next part of the slide. Okay, right now, so there is a postulates, measurement postulates given in the quantum physics or quantum mechanics. Okay, so what this postulate says is, before the measurement, quantum system can be expressed as, okay, so probably the notation is slightly different what people we use in the FDP. Let me explain what it is. You just to take a simplest situation where n equal to two-state system or a qubit system, that is one qubit. Okay, so in one qubit case, what you see, quantum system is A0 0 ket, A1 1 ket. Okay, so this I can write it as summation over I taking 0 comma 1 AI, okay, and yeah I. Okay, just to have a resemblance and the connection between these two, what I will do, I use an index as a n. I will not use index. Okay, n is equal to 0 comma 1 an. Okay, right? So inside the cat, I have written n as this. Let me use that differently. So which is phi n. Okay, so what is phi n by the way? Phi n takes when n equal to 0. Okay, let me do that. When n equal to 0, it will be 0 ket. Oh, it's just a 0, not a ket even. So it is there inside. Okay, when n equal to 1, it is 1. Okay, right? So this is just two qubit system when I explain. And if it is a in general n qubit system, summation of n, an, phi of n, where phi n could be what? If n dimensional system means, okay, how many zeros will be there for one of the bit? Okay, one of the bit would be 0 0 0 n times. Okay, right? So that is n equal to 0. Okay, let me remove this. N equal to 0. N equal to 1, I have few zeros which are n minus 1 times, and last is 1, that is phi 1. Okay, what is phi 2? Phi 2 would be 0 1 0. Okay, so here these are n minus 2 times zeros. Likewise, I can have how many number of quantum bit states I will have? I'll have 2 to the power of n bit states. Okay, so I'm sorry. Generic n qubits means generic n qubits means it will have 2 to the power of n states. So n running from 0 to or 1, okay, 0 to 2 to the power of n minus 1. Okay. Okay. Now, this is how we explain a quantum system in general. Remember, okay, so this is also written in the form of inner product. The probability amplitudes are written as the nth inner product between actual quantum state to that particular bit state. This is a bit state. See, this is a bit state. Now, how did we get this notation is, okay, remember, we will need to use few more things to understand that. Okay. Now, yesterday I discussed about computational basis. Okay. Computational basis, which is 0 ket and 1 ket. Okay. So, computational basis is 0 ket and 1 ket. Okay. Now, yeah. What is this computational basis? Interestingly, if you go and find the eigenvalues and eigenvectors of the Z gate, okay, so eigenvalues and eigenvectors of Z gate, okay, if you just take a Z gate who's having eigenvalues 0 and 1, oh, sorry, plus minus 1, the eigenvalues are plus 1 and minus 1. The eigenvectors are 0 ket and 1 ket. What I mean is, if I take as an act on 0, I'll get plus 1 into 0. If I take a z act on 1, I'll get minus 1 and 1 ket. So you know the eigenvalue equation. A matrix acting on eigenvector is equal to eigenvector multiplied by its eigenvalue. So this is a eigenvalue equation. Okay, right? Now Z gate has a eigenvalues plus minus 1, eigenvectors 0 ket and minus 1. So that's why the 0 ket and 1 ket are called eigenbasis of Z gate or Z gate or Z matrix. Okay, matrix. Fine. Now we are representing our quantum system in the eigenbasis of Z gate. You remember that. Okay. Now the question is there any other basis into which I can represent the quantum system? Yes, we can do and representation uh, right. So there is another basis called, okay, plus and minus ket basis. By the way, you just take this plus ket and minus ket. Okay, by the way, what is the plus ket? Plus ket is 0 ket plus 1 ket divided by square root of 2. Minus ket is 0 minus 1 divided by square root of 2. Now, if you find the vector notation of this one is 1 by square root of 2, 1 minus 1. This is a column notation or vector notation of these two vectors. Remember, they're orthogonal, okay, and also normal, means their length is 1. So are they orthonormal? So that they satisfy to be a quantum bit states, quantum basis. I can use them to represent a given quantum system. Now, a quantum system representation would be some A into plus ket, B into minus ket. Okay. So here I am representing the quantum system in a different basis. Now remember, earlier 0 ket and 1 ket are the basis of Z gate. Now is this plus ket and minus ket are basis of some other gate? Yes. The question you can ask is, okay, plus ket and minus ket, are they basis of or basis elements of any other quantum gate. Okay, the answer is yes. Which gate? X gate. You just take X gate matrix. Okay, if you find its eigenvalues, again they comes out to be +1 and -1, just like Z gate, and the corresponding eigenvectors, if you see, these are plus gate and minus gate eigenvectors. Okay, and minus gate. How do I check? You can check, you just take a X, multiply onto the plus gate. What do you get? You simply get the plus gate as it is. We know that X gate acting on 0 gives 1, X gate acting on 1 gives 0. When X gate acts on plus gate, I'm going to get plus gate only, because there is a positive relation between 0 and 1 inside a plus gate. Okay, X acting on plus gate, what do I get? 1 plus 0 divided by square root of 2, which is a plus gate as it is. But the situation is different when I take X gate acting on -1 gate. What happens in that case? Okay, by the way, what is a minus gate? Minus gate is 0 minus 1 divided by square root of 2. When X gate act on minus gate, what do I get? 0 becomes 1, 1 becomes 0, which is, minus of minus gate. Okay, so I can write down X acting on minus gate gives me -1 into minus gate. X gate acting on plus gate gives me +1 multiplied by plus gate. Therefore, the plus gate and minus gate together forms a basis for X gate. So you can simply say a plus gate and minus gate are the eigenbasis of this particular X gate. Okay, right? That is understood now. Now, in quantum mechanics, yesterday I was talking about to measure something you needed probes. Okay, right? So the probes are the tools to measure something. Okay, now the question is, you see, the quantum state is made up of or prepared with plus gate or 0 or 1. Okay, how do you know? Right? Okay, so okay, this is the quantum state. Two different kinds of quantum states I can have, right? So whether it is made up of 0 and 1s or plus and minus 1, how do you know? You need to know a measuring process where I can go and measure and measure whether it's in plus gate or minus gate. I can do that. Luckily for me, yesterday I was talking about projection operators would help me to find the vectors are formed in 0 and 1 or plus and 1. So now for a Z gate, there is a projection operators constructed out of its own eigenbases. Okay, so this is eigenbasis for a Z gate, and the corresponding projection operators are 0 outer 0, 1 outer 1 is a projection operators. In the case of X gate, whose eigenbasis is plus gate and minus gate, okay, projection operators are plus outer plus, minus outer minus. Okay, so these are the projection operators which would help me to find whether the given quantum state is prepared in 0 ket or in 1 ket. Okay, so I am talking about the basis, eigenbasis. Okay, so using the eigenbasis, you can write down the given quantum state. That is what actually projected here in the third slide. Okay. See here, what was projected? Okay, I could save it. I think I wrote something and it lost. I think, yeah. Right. Anyway, doesn't matter. Okay. So here you see, and this is the quantity which is AN is equal to, you just take inner product between the bit state, nth bit state with quantum state is going to give me the corresponding probability amplitude. Okay. An example, if you want, you can just consider quantum state is alpha 0 plus beta 1. You know, I want to find alpha. Okay. To find this, what do I do? Its corresponding bit state is there now. You multiply the quantum state with that. How? Take 0 quantum state. What you will get? Okay. What you will get? Inner product of alpha 0 ket plus inner product of beta 1 ket. Beta and alpha are constants. I can bring it out. Okay. So this quantity is going to be 0 and this quantity is going to give me alpha. Okay. So see, I got the alpha in terms of inner product between actual quantum state to its corresponding bit state. So that is what here shown. Okay. I hope you understand now. Now, yeah. Okay. There is problem with the. Okay. Yeah. Okay. Let me reopen the file. Where is the file? Okay. Yeah. Yeah, it is got saved anyway. Right. Now, so the postulates of quantum physics says the state is represented like this when measuring by an observable A. Now, observable A is what? In our case, the observable is, in our case, the observable can be Z gate or X gate. Okay. So these are the gates which help me to create the projection operators with the projection operators 0, 1 or the projection operator plus k or minus k, minus, plus or minus. Okay. So when I use the projection operators and measure them, the outcome yields one of the eigenvalue. One of the eigenvalue AN. We got earlier one of the eigenvalue alpha. Okay. Right. So, and correspondingly, the system immediately collapses to the eigenstate, corresponding eigenstate. Now here I am not seeing into which state this is collapsed. How do I know? What you take? You just take the quantum projection operator, act on the quantum system. You would see where it has collapsed. Okay. Yesterday we saw that. Now, let's say I want to know. Okay, so there is a difference here. Okay, this is a italic P. Italic P refers to the probability, and regular P, capital P, refers to the projection operator in our case. So please don't get confused. Okay. Now, if you want, you can write a small P for projection operators. Okay, sorry, probability. Now, the question is, what is the probability of obtaining a given constant AN or eigenvalue AN is you simply take the absolute square of alpha divided by psi inner psi. You know why this is required? So by any means, if the quantum state is not normalized, this quantity would take place. This is a normalization factor. Okay. Normalization to ensure we are dealing with quantum systems. So all quantum system must be of unit length. Okay. So this is how we are going to find what is the probability of given quantum system is falling into a particular quantum state. If it is falling in, with what probability it is falling in, how do you find? First, you multiply the quantum state with the corresponding bit state and take its absolute square and divide it by norm of that quantum state vector, and you will get the probability. Okay, so there are exceptions here. If the system is already in the eigenstate, the measurement yields an with certainty of P1 without changing the state. So what I mean here is, so instead of quantum state being in a superposition, okay, let's say if it is a final state, it is in zero state. It is no more superposition state, it is just a single bit classical state. If that is the situation, in that case, what happens? If you just make a bit state inner product with a quantum state, what do I get? Inner product between 0 with a 0, I'll get 1. So that is what the probability 1 they're saying. Okay? So with the probability 1, we will get that. So that is an exceptional situation. Only I'm talking about the scenario where we are existing or keeping the system in a superposition. Okay, right? Now coming back to using a tool, measurement tool. Okay, so we use the measurement tool several times to just to know exact information, because the quantum mechanically we may not exactly measure, okay, in one stage or in one step. So we have to do several iterations to make a measurement on the system. Since it is probabilistic in nature, not every time. So if a coin is falling into head or tail, how do I know with what probability it will fall into head and tail? How do I know? What I do? I make several tosses and then catch it, and I will. Okay, fine. So we need to do several attempts, right? So, and then out of all the several attempts, whatever the result we get, from those results we'll take the average. Okay, that is also called taking a mean value of that particular observations. Okay, average average result. So same thing would apply here. Average results of many measurements on identically prepared systems. Remember, identically prepared systems. Okay, right? Either you toss the coin several hundred times, or take all same 100 coins, toss them in one shot and make the observations. From there you find out what is the probability of this coin falling into head and tail. So right, so then while doing, I use the measurement. Okay, I use either side, multiply it with okay, on either side you use the measurement operator, and sorry, I think it was not recorded still now. Okay, okay, so the measurement average is taken as inner product between the quantum state and the new state when I make a measurement using operator. Okay, A acting on psi probably gives me some state. That state we take an inner product between the old states. That is what I mean by expectation value. Always will have a denominator with the inner product just to ensure it is being normalized. Now the result, what is the result it will be? It will look like summation over an. Remember, where ANs are the eigenvalues corresponding to this eigenvector, sorry, matrix A, and P's are probabilities. what is the probability of getting that particular eigenvalue is a p. So far we are using a small p for probability. Let me use that. Okay, right? So the physical interpretation is, if you prepare n identical systems in the same kind of a quantum state, you measure on that using an operator A on each one of them, and if you average out the results, then this converges to a expectation value or a mean value of A. In a classical world, you find the heights of all the students in the classroom and you sum them and divide it by overall number of students, and you will get the average of each student, average height of the class. Okay, the same story here. What we are doing, we are finding the averaged result. Okay, right? So let me go to the next part. Okay, and there is some physics here. What it says is, okay, right? So there is something called conservation, probability conservation and current density. Okay, so there is a probability density is usually written by what? Just absolute square of a quantum system. Okay, which is going to satisfy the continuity relation. You know, in continuity relation, so the continuity relation actually is there. Okay, even in the case of electromagnetic fields where the current, the charge is varying in time, it is going to give a continuity relation. The same story would also apply here, where here the probability current density is, J is a probability current density, which is actually connected to the quantum system and its gradients. You see, there is a quantum system, gradient of complex conjugate of a quantum system, okay, which comes out to be, quantum system is a complex number, so we will have the imaginary part of that some product. Okay, so what is this says is, this ensures probability is conserved, probability doesn't disappear, it flows. Okay, flows from, whether it's something suppressed here probability wise, it is created somewhere else. Sorry. Okay, so this is just for a physics point of view, and the most important thing here is, okay, we want to know how much measurements we can do. Okay, and up to what extent without disturbing the quantum system we can do the measurement, and that is what we want to understand in to a greater extent. Okay, so meanwhile, let's see some questions here. How should I understand, Lakshmana Rao is asking, how should I understand the following one? Is it the single entity is oscillating or traversing across different energy states? Yeah, you are right. Okay, right? The single entity is actually the electron is fluctuating or oscillating between, okay, the ground and excited state. So that is what the superposition state is, right? So where 0 is the 0th energy state, 1 is the first excited state. Okay, right? But you are taking an example, different heights of different persons in the analogy. I'm asking the above in the context of measuring the quantum state. Yes. So we should mind one simple thing here. I'm taking analogy of taking average of some measurements. Okay, right? So usually what is the average height, or let's forget about the average height. So what is the class average of particular in exam? In an exam, what you do? You sum all the total values obtained by all the students divided by total number of students, you are going to get the average. Okay, now I have a quantum system psi1, I have a quantum system psi2, I have a quantum system psi-n. Okay, I will just find the measurement, I will make a measurement of Z gate basis, or use a tool which is made up of Z gate, and make an observation of the psi1. What do I get? I'll get alpha and beta 1, which is comes out to be square root of, let's say, 40. This is square root of, let's say, 60. What I am doing, I am just writing in terms of probability. Alpha 1 square is 40%, beta 1 square is 60%. Similarly, I make a measurement on psi2. This time what I'll get? Alpha 2 I'll get 39 per square root of, beta 2 I'll be getting 51, 61, I sorry. Similarly, I make a measurement even on the nth system. Okay. This time I'll get alpha n, let's say, what do I get? Alpha n is something like 47. Beta n I'll get 53. Okay. I started all of them very close to 40, 60, but because of the environment effect or something, they got changed into this form. Now you see here, I made a measurement on all of them. I am getting out of n systems, some of them in the ground, some of them in the excited with corresponding probability amplitude. If somebody asks you, what is the average? On an average, what is the chance of, if I close my eyes, pick a atom or a quantum system from this group, what is the chance of my system, okay, existing in the ground state? What is the chance? So how much probability with it will exist in the ground state? So how do you find out? You take alpha 1 square, you sum it. You take alpha 2 square, you sum it. You go up to alpha n square, you sum it, and you divide it by n. So which comes out to be 40, 39 plus so on, 47 divided by, let's say, n. This gives me the average probability, okay, to find the system in zero state or a ground state. Okay. So this is the averaging out even in the quantum physics. So that is the example which I have taken. Okay. Now we need to relate this averaging out. See here, this is the averaging out. This is average. Let me put that average symbol. Okay. So this is equivalent to our expression here. What is the expression here? Where is that? Yeah, here. So this is the expression. Okay. So now, okay, wait a minute. So this is equivalent to expectation value of given operator. In this case, expectation value of Z operator. Okay, right? I hope I made this clear. The analogy is not equivalent. This is just used to understand. Remember that. Okay. So it's exactly 3 o'clock. Okay. So what we will do, just quick break, 5 minutes break we'll take, and we'll come back and we'll finish this remaining part. Okay.
Okay, sir. Thank you. Thank you, sir.
Yeah.